Okay, recording is started. Share my screen. Can everyone see the title slide? Differential mode conducted emissions.
Yes.
Okay, so today's session is going to cover conducted, the repeat of yesterday's session, by the way, but it's going to cover conducted emissions, differential mode, and common mode. So I have two separate slide packages here, but we'll cover the theoretical portions of both today. Next week we'll go back in the lab and it'll be more of the workshop portion, and I'll show you how some of these things actually work in the lab when you're actually running these tests. So with that, we will start with Kirchhoff's current law. Kirchhoff is just the messenger. It's really Mother Nature that says that all currents will return to their sources, or the way it's traditionally stated, all currents into or out of a node, the sum of all currents into or out of a node must equal zero. But from an EMI perspective, it's helpful to just think of it as all currents must return to their sources. If you have a source of current, it must come back, and it will come back. And so current will follow all available paths in inverse proportion to relative impedances. It will not follow the path of least resistance. I wish they had never taught us that, because it's an incorrect statement. It's only almost true at DC, but it's not even really true then. So if you, simple example, maybe I'll update these charts to show this at some point, but you take a 1 volt source and you put a 1 ohm load across it, you'll get 1 amp through that 1 ohm resistor. You put a 1 kilo ohm resistor in parallel with the 1 ohm, saying that the current follows the path of least resistance would imply that all of the current still flows through the 1 ohm resistor. And clearly that's not true. You're going to get 1 milliamp through the 1 kilo ohm resistor. And if the 1 amp is the intentional current that you want flowing through that 1 ohm load, whatever it may be, a motor or something like that, that's not your problem. That's the current you want flowing in that load. But that 1 milliamp flowing through some leakage impedance of a kilo ohm might be your bigger problem. So, the current is not following the path of least resistance. It's following every available path that it can find. So this current flowing the path of least resistance is really one of the worst lessons we're ever taught as electrical engineers. So the true statement is more of a mouthful, but it really is. It follows all available paths in inverse proportion to relative impedances, and it will be a function of frequency. So like capacitive paths are going to have lower impedance as the frequency goes up, and they will play a much more significant role in where the currents can flow as you go up in frequency. So getting into the difference between differential mode and common mode currents, which is really central to this conversation. I'm going to take a simple voltage source. I'll just represent it as a battery here. So but you take a voltage source and a load, some load resistance out here. The differential, I think somebody's got a hot mic. Can you please mute unless you're asking a question? Okay, thank you. Differential mode current is, at least traditionally, what we think of as the current that returns to the source on the intended path. So if you take this diagram at face value, more or less, that it's a pair of wires. You have some conductor getting out to your load and then a return conductor back to the source. The differential mode current is that intentional current flowing on the intended path, right? A dedicated wire, maybe a ground plane. The common mode current is what we think of as any of that current that is following some other path, generally an unintended path. Common mode current is generally not desired, right? So it's some undesirable, unintended path for that current to get back to the source. So it could be, as I mentioned, capacitive coupling, or it could be even some resistance. whatever it is, it's some other path that current is finding to get back to the source. Okay. And the focus of the first part of the discussion is on differential mode, and we'll get to common mode, later on. So a traditional conducted emissions measurement is performed on each individual power wire. So here I'm showing the current probe around the send wire. And when you do that, when you put a current probe around a single wire like this, you're measuring all the current on the wire. It's going to measure both differential mode and common mode. And you have no way of distinguishing between them. You're just getting all the current on the wire. And we generally measure it separately on the positive and negative or send and return leads, which means you're making two measurements per the letter of the law per Mill Standard 461. So you're making two measurements, but you're not really getting to the quantities of interest. So going back to what we call the MEDIC handbook, written from Marshall Space Flight Center EMC Design and Interface Control Handbook. I think this dates from around 2000, maybe even earlier, maybe even the 1990s. So this is nothing new here. But in that handbook, they specify or recommend directly measuring common mode currents. So for a power interface, you run your feeder and return wires through the current probe in the same direction. That'll give you the common mode measurement. For differential mode, you run one of the leads through the current probe in the opposite direction. We generally default to the return wire, but strictly speaking, it doesn't really matter. You just run one of the wires through the probe in the opposite direction. That will cancel the common mode current and give you a measure of the true differential mode current. The significance here is that common mode current will provide a direct assessment of the risk of radiated emissions and crosstalk from a potential culprit cable. And differential mode provides you a direct assessment of ripple applied to the power bus. And we'll get into the weeds on that here, in this conversation coming up very shortly. So these are two different problems, and you want to know which one you're dealing with. And doing the measurements this way, you get directly to those quantities of interest. You know exactly which kind of problem you're dealing with, common mode or differential mode. Now, this differential mode measurement applies to primary power interfaces only, where the common mode measurement we do on all signal cables as well as power cables. And a thing to note here, the true differential mode current passes through the current probe twice. So the level that the current probe is telling you is actually is 2 times higher or 6 dB above the true differential mode current. Okay, so you have to take that into account when you're making your measurements and comparing it to a limit line. We'll get to that here in a little bit when we talk about defining meaningful limit. But another central point is this is also two measurements, but this gets you directly to the quantities of interest. So this takes no additional time to do than the traditional method of measuring each of your send and return power leads separately. But if you have an exceedance with that method, you don't know whether you're dealing with a differential mode or common mode problem. You don't know which one you're dealing with, and you likely have to go to these measurements as additional measurements to determine what, to further diagnose your problem. And so with this methodology, you go straight to these measurements of interest. And it takes, and in the long run, it's probably shorter, right? You're making your two measurements, and then you know exactly what kind of problem you're dealing with. So for differential mode currents, the concern is all about compatibility with the power subsystem. So we have a simplified representation of a power subsystem. So I'm just representing it by a battery again. And this is for showing my bias toward DC power buses on spacecraft, because that's generally what we're dealing with. Generally nominally 30 volts. Used to be 28 volts, but now we hang more around 30, 31 volts. but it's all the same basic idea. It's a battery dominated DC bus. The general principles still hold with AC power buses, and you have AC power distribution in whatever building you're sitting in right now, whether it's your home or office or whatever. I'll avoid any snide comments that it's probably not your home. So anyway, never mind. Moving right along. But if it's 60 hertz, 120 volts AC, it's the same general principles. It's just not a battery, but you still have some power source, and then a common source impedance getting to a common distribution point here. It's historically, or at least I have historically represented it as basically what looked like bus bars, which I think may be how it had been done traditionally, or platforms of the past. But whatever it is, there's some common distribution point. And a lot of Goddard programs, recent platforms I've worked on, the distribution point is actually just a PC board. It's probably a plane on a PC board with a large capacitor bank hanging off of it. But whatever it is, you've got some conductors with some impedance getting you to this distribution point. You're going to hang a load off of it. That's the ultimate thing you're wanting to do here. You have your loads that are actually doing the work of what your platform is supposed to be doing. So your load is going to pull some current to actually operate, some differential mode current. So it'll be the main thing will be whatever the DC current draw is for the load to operate, whatever, 1 amp, 2 amps, whatever it is. And then there'll be some noise current, some AC current rippling on top of that basically forms your differential mode conducted emissions. So you're going to you're almost certainly hanging multiple loads off the distribution point. So the combined differential mode conducted emissions, the combined current from all of these loads, is going to put some noise potential at the distribution point. And it's just going to be that total, this really is the total differential mode current times your common source impedance. And that's going to give you the total noise potential at the distribution point that everyone will see. And so that forms the basis of your conducted susceptibility limit. Okay, so your differential mode conducted emissions limits are generally pretty much almost always defined for individual loads. You're defining a load at, or a limit at, an individual box level, because you want to be testing one box at a time before you integrate on the platform. So you want to define some limit for individual loads, generally in terms of voltage or current. We generally prefer current. We'll be talking about that here presently. So an individual limit in terms of current, but the current to any individual load is not ultimately what's going to be seen by everybody at the distribution point. For susceptibility, what we care about is potential. What is the total noise potential shown here that everyone will see? So conducted susceptibility limits are generally defined for worst case composite voltage ripple at the distribution point. So it's not entirely apples and oranges, but it's not entirely apples and apples either. So you can't just look at a conducted emissions limit and directly compare it to a conducted susceptibility limit. They are related. You just can't compare them directly with each other. And I'll walk through how you can correlate these limits in a meaningful way instead of just arbitrarily pulling default limits out of a standard. So we'll walk through how to define meaningful limits for a platform, and it may well be that the default limits are fine, but you should at least walk through this thought process to determine if they are meaningful or if they're overly stringent or maybe not stringent enough. So that's what we'll do right now. So we start with what is the total allowable voltage ripple at the distribution point that all loads will see. Now, and I'll emphasize here, excuse me, just taking my last sip of coffee there. So I will emphasize here that this is an example to illustrate the thought process. And the thought process is what I'd like you to take with you, not the final answer. So when we get to a final graph, a final recommended limit, that's for the specific example I'm walking through with the assumptions that I'm making. So please don't take the final result as, oh, well, this is the thing that we should use always. It's the thought process to apply to your platform so that you're coming up with something meaningful. So we'll start with a total allowable, excuse me, a low allowable voltage ripple at the distribution point. And typically that's on the order of 1 volt peak to peak in the time domain. And that's, basically broadband across all frequencies theoretically. And that's pretty generous. We don't generally see, that much, right? A good power bus shouldn't allow that much. But that's basically our starting where we conservatively say all loads should be able to withstand 1 volt peak to peak ripple on the power bus. Then we go a step further, to say that because ultimately our traditional conducted susceptibility limits are defined in the frequency domain, and they're a bit easier to test, and they allow you to characterize your susceptibility as a function of frequency. So we generally, our default, at least in GEVs, is 1 volt RMS over the frequency range of 30 hertz to 50 megahertz. So clearly, if you take 1 volt RMS over that whole frequency range and integrate it all together, you'll get something considerably more than 1 volt peak to peak in the time domain. Clearly, right? But that this limit is defined to be conservative, and 1 volt RMS, a 1 volt RMS ripple is not really all that stringent. Like it's not very difficult to make sure your equipment is not susceptible to 1 volt RMS at any given frequency. And if it is susceptible to that, you probably want to know about it. So it is intentionally, a bit conservative. In fact, this is a lot less stringent than the default in the mill standard, because in the mill standard, they're covering AC power buses. They're, 120 volts or sometimes more. So some of those limits allow up to 6 volts RMS. And that's been one of our issues in the past when we've taken the default levels in the mill standard, which are defined for 120 volt AC power buses, and then apply them to a 20 volt DC bus, allowing 6 volts of ripple on a 28 volt DC bus is beyond ridiculous. So that's why in GEVs we've tailored that down to 1 volt RMS, because that's way more than you should ever see on a battery dominated DC bus. So anyway, that'll be our starting point, 1 volt RMS from 30 hertz to 50 megahertz. Now that's in terms of voltage. So we want to get to current limits for each individual load. So the next step will be to convert this aggregate voltage ripple to an aggregate current ripple using the power bus impedance. So it's just dividing that voltage ripple, the allowable voltage ripple, as a function of frequency by the source impedance as a function of frequency. Then, so let's look at power source impedance. We talked about this last week, but for review, any harness impedance, or it could be traces on your PC board getting to your distribution point, however you're doing that, when you've got a pair of conductors, and even if that's, a conductor and a ground plane, it's still 2 conductors. When you have a pair of conductors getting you from your power source to the distribution point, that will consist of your conductor resistance, the inductance between the conductors, because it will always be there, it's just a matter of degree. And then at high frequencies, you'll reach the transmission line characteristic impedance. Whenever you have 2 conductors, you get up to a high enough frequency, it will behave as a transmission line. So it will have some characteristic impedance for the geometry. And in the transmission lines session in the fundamentals series, I go into the gory details of how you can calculate all those things. So this model is a little more representative of how things work physically, where the resistance, each conductor has its own resistance and so on. But we can simplify it just for the purposes of analysis and calculations. We'll just combine all of these parameters on one lead, the positive lead by default. And so to just look at this mathematically, we see that we have our Z naught, our characteristic impedance, in parallel with R plus J omega L. So we work through the algebra, divide by Z naught, and then we have this R over Z naught here. R is typically milliohms, maybe tens of milliohms. Z naught is typically tens to hundreds of ohms. So R is generally much less than Z naught, so we can basically make that, turn that term to zero. I mean, make it go away. And so now we have this expression here. So we can graph this. And then, so what do we do with that? Well, I find it helpful to break this down into frequency ranges. So if you look at low frequencies where you basically set omega equal to 0, well, you're left with R. So the low frequency plateau is just the conductor resistance, which makes sense. Then in mid frequencies, you're going to be dominated by the inductive reactance, J omega L. And then at high frequencies, everything cancels out except for Z naught. So you have a high frequency plateau of your transmission line characteristic impedance. So this model will give you this curve. This is a typical harness impedance curve. Like it basically is always going to have this general shape, just determined by your R, L, and Z naught terms. So Mill Standard 461 specifies a default 50 microhenry Lisen. So the Lisens are typically defined by the value of the inductor. So here you go. They don't even bother with the low frequency resistance, by the way. They have your 50 microhenry inductance that is giving you the impedance on the slope part of the curve here. And then the high frequency shunt giving you the asymptote up here is provided by the 50 ohm termination of your measurement device. So it's not a physical 50 ohm resistor inside the Lisen, but it gives you a measurement port here, a coaxial connector. And you connect a 50 ohm cable to it and then go off to your measurement receiver or whatever device, but with a 50 ohm input. And you just do your Thevenin equivalent analysis, right? The source impedance that your device under test will see looking back in this direction, per Thevenin. I should probably add a chart on this, but you short out your power source, and at high enough frequencies, these you're shorting out this capacitor, so it doesn't really matter. This capacitor will basically look like a short circuit. You're left with 50 microhenries in parallel with 50 ohms, which is basically what you want. So that 50 ohms is giving you the terminating impedance, for your measurement device, for your measurement system, but it's also providing that high frequency shunt for your Lisen. Now, this 50 microhenry Lisen is intended to simulate the worst case power distribution wiring on large military platforms. So remember, it's a mill standard. It's intended for military platforms, aircraft carriers, what have you. Spacecraft are included in it, but they're included as one item of many. So the mill standard is covering a large variety of platforms, of which spacecraft is just one part. So on platforms like that, power has traditionally been distributed as a single wire 5 centimeters above the structure or chassis. And the structure is used as the intentional current return path, which we almost never do on a spacecraft. So this type of configuration, wire 5 centimeters above chassis, is going to have an inductance of about a microhenry per meter. Again, in other sessions, I show you how to calculate that. So it'll be on the order of a microhenry per meter, running as much as 50 meters to a common distribution point. And that's right out of the mill standard that's where they came up with this 50 microhenry standard. This is not realistic for Goddard platforms. This is not how we typically distribute power. I've never seen it done this way, in fact. So I've never seen a Goddard platform where it has ever been appropriate to use a 50 microhenry Lisen. And I've had people come in insisting that that's what they want to use. And those conversations get rather interesting. So there is an alternate 5 microhenry Lisen specified in the mill standard in the appendix. And it's pretty much the same topology, just with a 5 microhenry inductor. And that may be realistic for smaller platforms, but it's still kind of overkill, right? And I'll show you a picture in a little bit of what that 5 microhenry inductor looks like to show you what it takes to get 5 microhenries. It's not something that you get by accident. So for Goddard platforms, the power source impedance is more accurately simulated by a capacitor network. So we have this pair of 10 microfarad feed-through capacitors between each power conductor and the ground plane. This is an integral part of the standard setup specified by the old mill standard 462. And so that's part of the standard suite of equipment in any EMI laboratory that's been around for any length of time. Even if they haven't been around all that long, they still should have a pair of these things. Our lab has several pairs because we've done any number of tests where we're testing multiple power feeds at once. And the intent is to provide a standard source impedance down to about 20 kilohertz. So just doing the math of 1 over j omega c, these capacitors will give you about an ohm of reactance at 20 kilohertz, approximately. It might be 1.5. Haven't refreshed the math recently. But on that order, okay. So we also, for DC power buses, for what we do on spacecraft, we add this 10,000 microfarad line-to-line capacitor, and that extends that standardized source impedance down to 30 hertz, which is the lower end of the frequency range for the tests that we do per mill standard 461 in GEBS. Now you don't want to use this on an AC power bus, like 60 hertz or 400 hertz that some platforms use. That won't work very well. That will effectively short out or severely limit your power, right? It'll kind of act as a filter. You don't really want to do that. But for DC, it's fine. And basically what it's doing is that it's acting like a battery. It's giving you a very low impedance as a battery will. And these 10,000 microfarad capacitors are readily available and inexpensive. I've bought 3 or 4 of them over the years for I think $100 tops. So any EMI lab will already have these, the feed-through capacitors, and the larger capacitor. I'll have some pictures later. I'll show you here in a little bit. But it's about the size of a large beer can. I like to say it's like a can of Foster's Lager or a motor oil can or something. But they're readily available, inexpensive. You can get them in a couple days for $100, where a custom Lisen might cost you $10,000. So if anybody tells you that it's really cumbersome and horrible to implement this capacitor network instead of a Lisen, that's simply not correct. You got a lot of you can certainly push back on that, and I have many times. So so now we'll walk through how do we come up with a meaningful set of limits using this 5 microhenry Lisen example. Now I've already said that this is overkill for most Goddard platforms, but it provides a ready example, for walking through this with a known controlled impedance to get a good correlation between conductive susceptibility limits and emissions limits. Okay, so one thing to note here is if you're going to use these Lisens, which are one thing I forgot to mention here, I did talk about this last week in the overview section, but going back to, yeah, here we go. Okay. The traditional, or the way I showed this impedance model here, this type of schematic really is a line impedance simulation network, which is one of the two definitions of LISM. So this is defining a differential impedance between your send and return conductors. And a LISN representing this type of impedance generally looks like this and is a self-contained box. One of the ISS LISNs that we use is like this. But what we have here for the 5 microhenry LISN and the 50, the impedance is with respect to structure, and that's called a line impedance stabilization network. So they're similar, but they are different, and you need to pay attention to which one you're using. They're used more or less, I mean, you're putting both in series with your power feed, but you need to make sure that you understand which one you are using. And if you're using a line impedance stabilization network like this, then you need one in series with each power feed. So you need 2 of them. So you'll have one in series with the positive lead and one in series with the negative lead. So the LISN itself does not include line impedance or line resistance. So I'm just going to assume 50 milliohms for the sake of discussion. Okay, so we have our 5 microhenry inductors and then our 50 ohm shunt impedance at high frequencies. And we'll just assume 50 milliohms of conductor resistance on each leg. So a total resistance of 100 milliohms. So when you're looking at your total impedance curve here, remember you've got to double each of these parameters. We're calling them 5 microhenry LISNs, but you're using 2 of them. So you have 10 microhenries of inductance and then a total of 100 ohms of high frequency impedance here. Okay, now if you just think about this for a second, if you have 100 milliohms of lead resistance and you've got a total DC current draw on a large spacecraft on the order of 100 amps, which is not too outlandish, probably fairly typical actually. Well, 100 amps dropping across 100 milliohms is going to give you a 10-volt drop. So I don't know anybody who's going to want that. That's a lot of power to just drop across your power distribution impedance. So it's just something to look for when somebody specifies a LISN impedance. If you see a resistance on this order, and I've seen resistances of 100 milliohms or more, it's an indication people may not really be thinking too much, that they're using some default LISN that they've always used. So anyway, I'm just going to use this for the sake of discussion. Okay, so here's our LISN impedance, total LISN impedance for 2 of them. So going back to our default conductive susceptibility limit of 1 volt RMS over this frequency range, that's really where you need to start, right? Because if you can withstand, just again a silly example to illustrate the point, if you can withstand infinite amounts of ripple on the power bus, then there's nothing to talk about, right? It starts with what is your susceptibility concern? What do you want to limit? What is your limit for how much noise you're going to allow on the power bus? Because if you're allowing a lot, then it means you need to put additional filtering in all of your loads and all that sort of stuff. It's kind of all part of architecting your system. But 1 volt RMS is not a terribly stringent limit. People should be able to filter that and so forth in a reasonable way. So that's what we're starting with. 1 volt RMS, 30 hertz to 50 megahertz. So that's our voltage limit at the power bus. So we're going to divide this by our impedance curve. So since it's a constant 1 volt RMS level, that makes it pretty straightforward. We're just taking 1 divided by all of these numbers across the frequency range. So we get a curve that has an inverted shape. So we're allowing 10 amps of ripple at the low frequency. And this is aggregate for everything on the bus, by the way. We're working up toward an individual limit. So we're allowing 10 amps at the low end, low frequency end, and 10 milliamps at the high frequency end. All right. So now that is our aggregate current ripple that we're defining at the distribution point. Okay. So now we want to apportion that to each load as a function of current. And we can do that on a per ampere basis. So on most of the platforms that I've worked, 1 amp is a fairly typical DC current draw for the load. So we can just kind of normalize it to a 1 ampere current draw. That'll be our minimum. So anything that's less than 1 ampere, we'll just kind of round up to 1 amp. So we'll apportion this aggregate current ripple, on a per ampere basis, right, to get an individual limit for each load. And so to do that, you divide that total allowable aggregate current ripple by the total current capacity of the bus. I'm going to use 100 amps as an example here. It makes the math easier, but it's also it's in the ballpark of a typical mission. In fact, for RST, when I worked through this for some waiver requests, that's where that came from, really, at least most recently. That 100 amps is about what we're using on RST. So we divide this curve by the total bus current capacity, so 100 amps in this example. Then we convert it to dB microamps for a component level true differential mode limit per ampere, that is. But remember that when you make a differential mode measurement, the current is passing through the probe twice. So what you'll actually measure is 6 dB higher than the true differential mode current. So we'll add 6 dB to that whole curve. That's the way we do it at Goddard. If your measurement system allows you to add that 6 dB factor into your profile to back out the true differential mode current, you can certainly do it that way, but one way or another, you have to account for that 6 dB factor. And we do it just by adding 6 dB to the limit. Okay. So when you work through the math to get the true differential mode limit per ampere, you get this dashed red curve. Then we add the 6 dB to it to get the dark blue curve. So that's the apportioned differential mode limit per ampere. And so if you have more than 1 amp of steady state current, you would just add 20 times log to base 10 of whatever that steady state load current is. So if it's 2 amps, you would add 6 dB to this limit. Now your mileage may vary, can't emphasize enough. It's the thought process that is important here, not the final answer. Don't take this curve and say, oh, that's what I should use. If you go through this thought process and it applies to you, great. But it's the thought process, not the final answer, that's important here. So everybody still with me, by the way? Just checking in. Hello? Is anybody there?
Yeah, we're here.
Okay. I usually say it would be more disturbing if your mics were hot and I heard snoring. So if you're gonna snore, make sure you're muted. Anyway, Mill Standard 461 test method CE 101 from 30 hertz to 10 kilohertz is the default. That specifies a current measurement. Okay, so you have a current probe. This is showing it measuring it on the return lead here. This is the default technique where you're measuring one wire at a time. And then the CE 102 test method, the higher frequency portion, 10 kilohertz to 10 megahertz, specifies a voltage measurement across a LISN. So this we would be using, if we use our 5 microhenry LISN example, you would tap off of those measurement ports there. I'm sorry, that's down here. I made the same mistake yesterday. There's the signal output port. You would tap off of that. You need to make sure you put a 50 ohm termination on the one you're not measuring at a given time, right? So you still need give that 50 ohm shunt impedance at high frequencies. So you tap off of that and go to your measurement device. Okay. Now, a voltage measurement is going to depend very significantly on the power source impedance, which can vary across platforms. This is why I do not like CE 102. We'll talk about more of that here coming up. But if you're going to make a current measurement, which is what I strongly recommend, basically I require on any program that I have, that I have direct involvement in, do not use the CE 102 nomenclature. This is one of these cases about learning the language and being EMI literate. If you mention CE 102 in any capacity, but then you're doing a current measurement, you're causing a lot of confusion and it's going to cause people to swirl around to make sure they actually understand what you're doing. I've seen this where people will say, we're doing a tailored version of CE 102 that's a current measurement. So please don't do that. If you say CE 102, this is what your lab folks are going to be envisioning, and this is what they will set up for. They'll put the LISNs in place, and they're going to be looking to do a voltage measurement. If you're doing a current measurement, CE 102 should not appear anywhere in your test plan, procedure, or test report. Can't emphasize that enough. It confuses the hell out of things, and that nomenclature should not be used if this is not what you are doing. Okay, so the differential mode current measurements are made across the feed-through capacitors. So getting back to our capacitor network. Okay. They provide a worst-case measurement of current emissions that are largely independent of the source impedance. So again, the capacitor network is intended to represent a battery. So as basically as low an impedance as you can get. So whatever current emissions, whatever current noise the EUT is going to produce, the low source impedance will be able to provide that current. And so you won't be providing some kind of impedance here that will artificially limit whatever current the EUT may draw. So different current probes are required for different frequency ranges, but otherwise the methods are identical, right? The same basic setup holds here. So for CE 101 differential mode, we extend the upper limit to 150 kilohertz. And then CE03 from mil standard 462 is what we generally apply in the higher frequency range, from 150 kilohertz to 50 megahertz. Okay, so this is one place where people say, well, you say you're doing mil standard 461G, why are you going back to 461C and 462? Well, this is the reason that for our types of platforms, a current measurement in the higher frequency range is much more meaningful and directly useful to us. CE 102, for all the reasons that I've said, is not a meaningful measurement and is not desirable. It's non-trivial to try to correlate what you measure with CE 102 to a typical power bus that we have on a spacecraft. So where I say if you're doing a current measurement, call it CE03, not CE 102, because that is what you are doing. So again, the CE 101 and CE03, tailored for differential mode as shown here. The methods are otherwise identical besides just a different current probe for different frequency ranges. This shows the general setup per mil standard 461G figure 2. The current probes will be placed near the LISNs if you're using them, or the capacitor network for our applications. And then if you're using CE 102, the voltage measurements are made at the LISN output port. And I'll want to make the same statement that I made at this point in the presentation yesterday. I don't want to sound like I'm thoroughly disparaging CE 102. That's not really my intent. I think the general idea of the measurement makes a lot of sense. It's just the specific implementation is not really appropriate for what we're generally doing on spacecraft. So what I mean by that is we are ultimately what we are interested in are is the voltage ripple at the power bus. And with CE102, you are making a direct measurement of voltage ripple. So I get that intent. I think that's a good idea to start with. It's just that if you're doing that with a 5 microhenry inductance in series, when the impedance on your power bus on a spacecraft is likely to be much lower than that, then it's not really an accurate, it's not really the best fit for what we're trying to do. So I say, I think it's a good measurement technique, a good test method when it's applied appropriately. And that's a statement across the board. Any test method when it's applied appropriately is a good test method. But when you're fitting a square peg into a round hole, then it's not. So I think it's important to understand the CE102 test method, because you may encounter a platform where that's the required test. And we've had some programs come in and say that is what they are applying. And if you can't convince them otherwise, that they're holding the line and saying, nope, you're doing CE102, well, okay. That's what you need to do, and you need to understand how to do it properly. So moving right along.
So John, real quick. So basically what you're saying is the 5 microhenry is not, it should be something, what should that be for a typical spacecraft?
Is that Mike?
Yeah, it's Glenn.
Oh, hey, Glenn. You sounded like Mike Mann. That was a good Mike Mann impersonation.
Oh, okay.
So, I'm sorry.
He's got dark hair. Mine's a little lighter.
Okay. Well, that's what I was saying. What for our platforms at this capacitor network is what we should be using. That basically replaces the LISNs in these test configurations.
Okay, so you don't want that 5 microhenry. You want this.
Right.
For the CE102.
Well, for CE03. It's
Oh,
only you're calling it CE102 if you're using the LISN and making a voltage measurement out of it. If you're making a current measurement, and especially if you're making a current measurement with the capacitor network, it's CE03.
Okay, so I guess going back to CE102, if we have to do it, what's the LISN really going to look like for a typical spacecraft?
Well, the platform should specify what LISN is appropriate for their spacecraft. But like the 50 microhenry LISN, I've never seen any platform where that made any sense. Some people still insist on using it, but the project, if they've done their homework, they should specify what LISN they want to use, if any. That needs to come from them. If they say no, we want to use a 5 microhenry LISN, or if they have a custom LISN that they may specify, they need to identify that. That's not up to the test team to say what's the appropriate LISN. That needs to come from the project. So, hey, that's as much as I want to say about LISNs here.
Okay.
Besides the capacitor network. So the general setup for GEVs shows the capacitor network replacing the LISNs. We'll place the current probes near the capacitor network. And so this is just showing the two main current probes we use for so it's CE101, the low frequency range. We use this Pearson 3525 current probe. Nothing particularly special about it. I mean, just it's a good workhorse current probe, but just any current probe that works in that lower frequency range, and gives you the performance you need. But this is the one we use, and you see the one of the leads is going through the current probe in the opposite direction, looped through, and then this electrometrics current probe for the higher frequency range. And here you can see this red lead is what's looping through the current probe in the opposite direction. So if you look in the appendix of Mill Standard 461, it goes through some alternate ways of doing things with a 5 microhenry LISN as opposed to the default 50 microhenry. That it gives you this graph showing a set of curves, and so we generally we're generally using curve number 2 for a 20-volt DC bus. Because here again, mill standard, so it includes 115 volt AC, well, 400 hertz here too. So it's dealing with 400 hertz and 60 hertz power distribution. But we're generally using curve number 2, and here is that guidance where that low frequency plateau will scale with the load current. So I didn't make that up. That's something right out of the mill standard that you can and should scale that low frequency plateau according to the load current. It kind of makes sense, right? More current intensive devices should have a little less stringent limit, right? So if we look at this CE102 limit, and I'm going to relate this to CE03, so that's the ultimate point here. So this is the CE102 limit in the mill standard. Well, and you take the 5 microhenry Listen impedance at the low end at 150 kilohertz, that's right around 5 ohms or 14 dB ohms. So if we look at the CE102 limit in voltage, at 150 kilohertz, that's right around 70 dB microvolts. So to correlate this to a current, we just, in numeric terms, we're dividing the voltage by the impedance. In dB space, we're just subtracting the impedance, right? So we take 70 dB microvolts minus 14 dB ohms, that's 56 dB microamps. Well, why do we care about that? Why am I bringing that up? Well, that's what we have over here. This curve 2 reaches a level of 56 dB microamps at 150 kilohertz. So that these two limits meet up where one leaves off and the other one picks up. That's not by accident. The people who defined these limits did their homework and did this on purpose. And I know some of the people who wrote this document. So I mean, I know that for a fact. It's not just, my assumption. And so if we look to see the basic CEO3 limit, the limit at 150 kilohertz, it's 56 dB microamps. Again, all this was done on purpose. All these pieces fit together. So this forms the basis of our default differential mode conducted emissions limits in GEVs. So limits below 150 kilohertz are based on CE 101 tailoring guidelines in the mill standard in the appendix, the ones I just walked through. And that low frequency plateau shifts upward for higher currents just by adding 20 log of the load current in amperes. The limit extends to 150 kilohertz instead of 10 kilohertz, the default in the main body of the mill standard. And then the limit at 150 kilohertz is fixed and calculated to coincide with the CEO2 limit at 150 kilohertz based on the impedance of a 5 microhenry Listen. And the limits above 150 kilohertz based on the CEO3 limits of the old mill standard 461C. And we add 6 dB to this for a differential mode measurement. So that 56 dB microamps at 150 kilohertz bumps up to 62. So all of the limits across the board we just bump it all up by 6 dB. So if we look at this at the apportioned limit example that I walked through in the red curve here, and then compare that to the default GEVs limit for a 1 amp load, we get really excellent agreement up to a few hundred kilohertz. And then the default limit is clearly a bit more stringent at the high frequencies. So I mean, we have applied that default GEVs limit on a number of programs, and so if you've done this homework, this is actually the kind of thing I've written up in waiver requests. But if you do this kind of thing up front and define your limits according to this type of analysis, then you can give yourself a little more of a less stringent limit up here in the higher frequencies, and avoid a lot of time-consuming waivers, because waivers take time to write up and approve. Even if I'm the one writing them up and approving them myself, it takes time. So a word about the frequency range. Each unit on the bus generally has a switching DC to DC power converter. Its raison d'etre is to sample the power input at the switching frequency and then provide regulated stable DC voltages required by the circuitry in the unit, whatever it is you need, plus or minus 15, plus 5, plus 3.3, whatever. The DC to DC converter control loop generally addresses low frequency ripple. As you're, if you're typically these switching converters, the frequency is typically on the order of 100 kilohertz or higher. And so for the very low frequency stuff, 30 hertz up to whatever, few kilohertz, 10 kilohertz, you're significantly oversampling. I mean, you're sampling a DC level, right? But whatever that ripple is riding on top of the DC level, you're oversampling that by, at least an order of magnitude or so. And the entire purpose is to adjust the pulse, the pulse width, pulse width modulation to give you the desired output level, whatever is happening at the input. So that control loop by design is addressing low frequency ripple. The high frequency ripple is addressed by your input filters. You usually have a pretty significant EMI filter on the front end, of healthy capacitor bank, and maybe some inductance in series, prior to it. And so that filter knocks out that high frequency ripple before, so that it doesn't even get to the power converter. And we generally consider 50 megahertz to be sufficient upper frequency for any power quality concerns, because anything above 50 megahertz is just going to get squashed by those input filters and won't be an issue. So conductance susceptibility issues tend to occur at the mid-range frequencies, kind of in between the effectiveness of these two factors, of your control loop and the high frequency filters. So this is the stuff that we'll look at next week when we go back into the lab with the webcam and everything else. I'll just give you a little sneak preview that our basic setup, our EUT, is this interpoint converter that the power group, my neighbors here in building 20, they gave this to me. I should probably clarify whether they gave or lent it to me, but they provided it to me some years ago for this very purpose, to demonstrate how to do these types of measurements. I wanted a noise making thing, and this delivers the goods. Notice the complete absence of any filtering in here, and notice the non-Faraday cage. It's just a black plastic box here. It's not shielded, and there's no filtering. So when we actually show you some measurements, you'll get to see this thing sing, which is what I wanted, to be able to show how you actually make these measurements. So that's one that we'll get into some of the guts of that next week. One thing I'm going to show you here before we switch over to common mode. I told you I was going to show you the inductor in the Lizen. So this picture here shows you the pair of Lizens. So we have this workhorse power supply here, and it's going through the Lizens. We have a pair of them. And so this picture shows you what's inside. This has the lid removed. So there's your 5 microhenry inductor. That's really the business end of this thing. And then you have a couple of line to chassis capacitors. It's just the metal housing of the capacitor mounted to the chassis of the Lizen. Actually, only this one's mounted to the chassis. That one's isolated. But the point here is, this is what you need to get 5 microhenries. And depending on the size of your screen, that's approximately real size, approximately 1-to-1, at least on my screen. Just to first order, that's about accurate size. That's what you need to do to get 5 microhenries. So that's not, you don't get 5 microhenries of stray or leakage inductance. If you're talking stray or leakage inductance, you're talking tens of nanohenries, maybe 100 nanohenries. To get 5 microhenries, you have to mean it. And even that's just way overkill for the kind of inductance you're likely to see on a power bus. When you have a dedicated return wire twisted with your send wire, you're going to have, again, tens to maybe 100 nanohenries per meter. So, okay, I misspoke slightly. If you have, let's say you have 100 nanohenries per meter, and your power wiring, is running 10 meters, then maybe you'll get a microhenry. But we almost never have 10 meters to the distribution point. that would be maybe 10 meters to a given load. But that's not what we're talking about. We're talking about what is the wiring to a distribution point, which should be much shorter than that. So even microhenries of inductance to a distribution point is just not realistic for what we do. Now, if you think about the power in the building you're in, that wiring could be running tens to 100 meters from the service panel in the building to the section of the building where you are, where a bunch of outlets are ganged together. There could be a much more significant common source impedance there, because it's one set of wires, one running to the first outlet in the chain, and then those outlets in your office and maybe that whole group of offices in that corner of the building are ganged together, daisy chained together, running off of a very high common source impedance. That's where this kind of thing makes a bit more sense, where you have a very high common source impedance, where whatever noise you generate is going to be seen on that power bus by everybody. That's not what we do on a spacecraft. We run dedicated leads by and large back to as a point as close to the power source as possible. Basically, why power quality problems are very rarely a significant problem on spacecraft, because for that very reason. It's still a good idea to test for it, but when you've got a good low common source impedance, it's generally not an issue. So, anybody have any questions before we shift gears and go to common mode? Okay, are you still there?
Yep.
Yep, we're here.
Oh, yeah.
Okay. All right. Well, let's gears. Somebody do that on purpose. I heard a snore, or maybe it wasn't on purpose. What's that?
Yeah, it was on purpose.
Okay. Anyway, okay. Trying to think of a sarcastic rejoinder, and I'm stymied. So congratulations. All right. So a lot of stuff. Stuff in the first part of this is duplicated, because I initially put these together as two separate presentations. But here we are. I'll skip over the stuff that I'm duplicating. But emphasizing from last week's session, interconnecting cables are part of the EUT. Common mode energy in the EUT can couple to cables, and probably will, which can and will radiate. And then in the opposite direction, any incident radiated energy can and will couple to cables, which will then carry that common mode current into the EUT and possibly cause disruptions to your circuitry. The cables are most likely going to be your most significant or most efficient radiating elements, either from both an emissions and susceptibility standpoint. They will be the most efficient radiating elements in the frequency range where they are significant fractions of a wavelength. So typically, if you're talking a couple meters of cabling, that's typically in the range of tens of megahertz to a few hundred megahertz. It's once you get up into the gigahertz range that the box itself, like seams on the box and things like that, will be your most efficient radiators. But that's the significant part here, is that once you connect cables to this box, then they will sing in that lower frequency range, because they're longer and their resonant length. They will be resonant at lower frequencies than anything in the box by itself will be. So a properly designed box level test with flight representative cables, as they are required to be, and representative loads, exercises the cables as much as the electronics box. So there's really no such thing as a box only level EMI test, except when you're talking about maybe something like a cell phone not connected to a charging cable. But we are almost never testing anything like that. We're always testing something with cables connected to it. So if you shortchange the box level test, it only invites additional risk at higher levels of integration, and that basically defeats the purpose of any unit, or what I will call a subsystem level test. you want to flag issues at this level and address them before you integrate them onto the platform, because it gets a lot more expensive, time consuming and messy, and project managers don't like it very much if you have these kind of issues on an integrated platform that you should have found during these lower level tests. So when an EUT meets radiated emissions and susceptibility requirements on a military platform, there's generally a low risk of crosstalk. And it's because the default RE102 limit corresponds to common mode current levels on culprit cables that are way too low to pose a significant risk. RE limits that protect radio reception, which is the raison d'etre of RE102, are significantly more stringent than what is necessary to protect against cable-to-cable crosstalk, which makes sense, right? Your radio receivers are by design your most sensitive victim on the platform. They are specifically designed to be sensitive to very low RF signals. So if you meet levels that are designed to be compatible with radio reception, you're generally way lower than anything you need to protect against crosstalk, which is why there's no real specific crosstalk mitigation tests in the MIL standard, why we come up with them ourselves in GEVs. So outside of radio bands, the default limit may be relaxed. This is, to my mind, this is precisely the reason that RE102 exceedances have historically been the largest sources of waivers on many Goddard platforms, and why Rodney Dangerfield has been our patron saint. And I love Rodney, I love his humor, but I don't really want him to be our patron saint anymore. So most Goddard platforms do not use antenna connected receivers below 200 megahertz. So following this guideline, RE102 is applicable only above 200 megahertz on most Goddard platforms. And that's GEVs. When I show section numbers here, that's GEVs. In section 25232 of GEVs. So crosstalk is the dominant concern below 200 megahertz. And I love this quote from late great Henry Ott: "Conducted emissions limits are really radiated emissions limits in disguise. They're one and the same." So if we look at the RE102 test method, we have these different antennas we use in these different frequency ranges. One thing I'll point out here is the RE102 method specifies 1 meter distance from the test antenna to the setup boundary. I'll talk a bit more about this in the RE102 section or session coming up probably in a few weeks. But it has to do with the fact, I mean, even you just look at these figures, take them at face value. Obviously, they're not necessarily intended to be to scale, but approximately. You can see that an antenna of this size, 1 meter from the test boundary, is not in the far field. It's very much in the near field. So they pick just a normalized distance to make the measurement, but the test antennas are calibrated at that specific distance because you're not in the far field. And I went through this sort of thing in the dipole session, so you can feel free to review that. But there are just a lot of reasons that this 1 meter measurement distance is non-negotiable. If you're doing RE102 and you're using calibration factors for your antennas that are valid at 1 meter, that's what you need to do. Because if you mess with this measurement distance and try to use those same cal factors, you're going to get some errors in your results. For commercial testing, there are cal factors for 3 meters and 10 meters for much the same reasons. But anyway, the point is that you need to make this measurement at 1 meter. And I'll talk about that here in just a moment in the next slide, the significance of that. But we have an antenna configuration break at 200 megahertz. So that's what makes that a convenient place to say, well, okay, we'll do RE102 only above 200 megahertz. Generally, the lowest receiver we deal with is range safety at about between 400 and 500 megahertz. So strictly speaking, we could probably start there. But if we're gonna be hooking up this antenna in that frequency range anyway, we'll just go ahead and start at 200 megahertz, at least by default. So the dominant concern below 200 megahertz is cable-to-cable crosstalk. So here's where that 1 meter distance comes into play. RE102 and RS103 do not effectively address cable-to-cable crosstalk. This is very much square pegs and round holes when we try to do that. RE102, as I just said, specifies a 1 meter measurement distance. I have never encountered a cable-to-cable crosstalk problem at a 1 meter distance when cables are 1 meter apart. That just doesn't happen. We're generally concerned with crosstalk. We're talking about cables in the same bundle or very close together on the order of 1 or 2 centimeters apart. And any attempts to correlate a measured field at 1 meter to an expected field at a few centimeters is non-trivial and carries very large uncertainty, and that's putting it very mildly. Any of the stuff that you hear about, scaling it as 1 over r, 1 over r squared, 1 over r cubed, that's making a lot of drastic assumptions that are very inaccurate. The traditional equations for a Hertzian dipole are assuming that you're dealing with a point source. The equations are already, I have those in other sessions, but the equations for a Hertzian dipole are already very complicated, literally complex. They are complex numbers with a combination of 1 over r, 1 over r squared, 1 over r cubed terms, assuming you're dealing with a point source. So when you're 1 or 2 centimeters away from a cable that's a meter long, can you assume that's a point source? Well, of course not. So whenever somebody makes an RE102 measurement at 1 meter and then tries to correlate that to a field that for a box or a cable that's significantly closer than that, that is not a reliable analysis, and that should not be taken seriously. So this sort of thing is much more efficiently addressed with direct measurements of common mode currents on cables. So we can measure the emissions and we can characterize the susceptibility, and now we're dealing with apples to apples. Okay, so this is a repeat of the stuff from the differential mode section, so we can whiz past this. Now we're focusing on common mode. We've talked about this and this. Okay, so the nature of crosstalk. First, we'll talk about capacitive crosstalk or electric field. So you have some culprit conductor. This could be a bulk cable or a wire, whatever the case may be. But we'll model it as a single wire, but this could be a bulk cable. And that for cable-to-cable crosstalk, that's what we're talking about. So you have some potential, some noise potential on your culprit, and then you have a victim conductor nearby, victim cable, and on either, basically you're going to have some impedance to your signal reference on either end of it, so Z1 and Z2. And if you have conductors that don't have a conductive connection between them, there will be capacitance between them, always. It's just a matter of degree. If they're sufficiently far apart, then the capacitance isn't a significant factor, but it's always there. So you'll have some capacitance between the conductors, and so that you'll have that capacitive reactance, the familiar 1 over j omega c. Well, then you're also going to have the victim impedance to the signal reference is just going to be the parallel combination of these terminating impedances on either side. And so you're setting up an impedance divider. So the coupled potential is going to be the victim coupled victim potential, VV, is going to be equal to your culprit potential times your impedance divider. So your victim impedance, this parallel combination over, and it's really going to be a complex combination, but just simplifying it here for the sake of illustration. Actually, that is an accurate way to represent it here. But in any event, it's an impedance divider. So how do you deal with that? So with capacitive coupling, the most effective way to deal with that is with shielding. So you put a shield around your victim conductor. You will still have capacitive coupling, but the first thing that energy will see it'll see the capacitive coupling to the shield. So whatever noise currents are on there, instead of directly finding a capacitive path to this victim conductor, it'll find the shield, and then that current will return to the source on that path. So you put another shield around your victim, well, there will still likely be some residual energy that will find this capacitively coupling path. But now it's going to find this shield before it, quote, sees the victim conductor. So it'll find another path back to the source through that path, through the shield, instead of into the victim conductor. Okay. So the shield provides a low impedance path for noise currents to return to the source. That's the recurring theme here, that the currents will always return to the source one way or another. So if you provide them a low impedance path back to the source, that is what that is the path that they're going to want to find. Or most of it will find that, and you want to minimize how much of it is finding some other path that you don't want. So it's redirecting the noise currents. It does not make them go away. If you make them go away, like you knock them out at the source, then there's no need for shielding. There's no need to redirect the currents. But just important to recognize that when you put a shield on something, you're not making the noise go away. You're just redirecting those noise currents so that they have a lower impedance path back to the source, away from stuff you're trying to protect. So if you're concerned about this sort of thing, if you're concerned about noise potential on a culprit, we do have a way of measuring it. It's with this Fisher capacitive voltage probe. You put the cable through this, and it's a clamp-on device. You see the clamps right here. So you can measure the common mode potential on a culprit cable, and we've used this, from time to time. But it's a non-standard measurement, and there's actually a more efficient method, which is what I'll talk about now. This gets to inductive magnetic field crosstalk. So like when you're dealing with shielded cables at the system level, capacitive crosstalk, it doesn't tend to be your dominant concern. This is the capacitive crosstalk. It dominates like with traces on a printed circuit board and things like that. And that's a whole separate conversation. But when you're talking about crosstalk between cables at the system level, magnetic crosstalk tends to be more of what we're dealing with, is the dominant factor. So here again, we'll look at a culprit conductor, and then our grounding conductor, which I hate that term, but our signal reference, right? So it could be a wire, it could be the ground plane, but I'm just going to represent it schematically as a wire effectively here. So you'll have some current on your culprit conductor, and it'll generate some B field, magnetic flux density, using the right hand rule where your thumb's pointing this way, then fingers wrap around, and so the magnetic flux will be into the plane moving to the right. And so the total flux through that loop will be the surface integral of that B field vector through the surface. And then the inductance is defined as that total flux divided by the current that caused it. And that's the partial self-inductance of that culprit conductor with respect to the grounding conductor or signal reference. Now, if we look at a victim conductor, and we're going to ignore the culprit for just a moment. We'll come back to it here presently. But whatever current is on the victim conductor, I'm showing it going in the opposite direction here, but it will, again, using the right hand rule, it will generate magnetic flux going in this direction, coupling through, going to the left through the loop this way. And so the total victim flux, again, is the surface integral of the B sub V vector through that surface. So the partial self-inductance of that victim conductor with respect to that same ground or signal reference here is going to be that total flux divided by that current. Well, we can see from the similar geometry, we're talking about culprit and victim in basically the same bundle. We can say to first order that those inductances are approximately equal, the same geometry. Right? It's the same wire above the same signal reference, so it's the same loop area. To first order, we'll say that those inductances are equal. Those partial self-inductances are equal. So going back to our culprit current, we can say that all of that flux from the culprit wire is not only coupling into its own loop, but that same flux is what's coupling into the victim loop. All right, it's the same loop area for they're in the same bundle to first order, right? So that flux is going to induce a potential in the victim circuit, in that victim loop. We'll call that V sub V. So per Faraday's and Lenz's law. And the negative sign means that the potential will be such that it will counter or oppose or impede the incident flux. So if the incident flux is penetrating the loop in this direction to the right, then if you point your thumb in the direction of the opposing flux, pointing outward this way, then you wrap your fingers of your right hand in this direction. That is the direction of that is the polarity of the induced potential in the victim loop. Now, so it's important to emphasize this, that the magnetic coupling, magnetic flux induces a potential. We sometimes say that it induces a current in a victim circuit, and that's not entirely correct. The current is a secondary effect. The thing that it's most directly inducing is the potential, and then the current is a function of the impedance of the loop, which is the next point. But the thing that's induced directly is a potential. I mean, V equals d phi dt. That's what we learn, right? So now this coupled potential we can express as the mutual inductance between our culprit and victim, the culprit conductor and the victim loop. It's the inductance times di dt. So our mutual inductance times the time derivative of our culprit current, or to express it in the frequency domain, j omega m of m times IC. But again, because of the same geometry, we can, to first order, say that m, the mutual inductance, is the same as the self-inductance of each of our culprit and victim loops. This is an important thing, or well, it's a thing I'm sharing with you because I've seen this sort of thing in textbooks where they just kind of tell you this, that the mutual inductance is the same as the self-inductances of each of these loops, but they don't really explain why. And that's what I've painstakingly walked through here to help myself understand that, because I've just sort of seen this as a statement where they don't really explain why, and this is why. That it's when you've got a culprit and a victim that are in the same bundle with respect to some ground reference, that's where you can make this statement, that mutual inductance between the culprit and the victim loop, is essentially equal to the individual partial self-inductances. Everybody with me there?
Yep.
Okay. All right. So mutual inductance to a nearby victim conductor will, and here I'm violating the prime directive here. It'll induce a potential, but then the current is going to be determined by the impedance of the loop, which we'll get to here in just a second. But this is a bit like a transformer. In fact, it's exactly like a transformer, right? And so the current in the victim loop now is going to be this potential we've induced. Again, to first order, it's going to be dominated by the inductance. Right? If it's a purely conductive loop, then the resistance is going to be low. It won't be zero, but we can say that at the frequencies of interest, it's going to be the inductance that's going to dominate that impedance. So it's going to be j omega LV. But then the coupled potential, so that is j omega times the mutual inductance times the culprit current. Well, we've said that m approximately equals the self-inductance of both the culprit and victim. So the m and the LV terms cancel, the j omega terms cancel. So in the worst case, your victim current is approximately equal to the culprit current. So that's the worst case that we can assume, that we should assume that for cable-to-cable crosstalk, for wires in any kind of proximity to each other, cables in any proximity to each other, the victim current can equal the current that's on the culprit. So that's our worst case assumption going forward. So inductive crosstalk may be directly and efficiently addressed with direct measurements of common mode currents on cables. So we can measure the emissions, we can characterize the susceptibility with the CS114 test method. And fear not, I've got a whole session on that planned. And these are done with clamp-on current probes. You clamp on a current monitor probe to make emissions measurements, and then clamp on an injection probe for susceptibility testing. And you can see they're basically the same type of construction. It's just in terms of size, because they both work. They both use Ampere's law and Faraday's law. And so with a monitor probe, you're running your cable through the aperture, and you're not directly measuring current. What you're measuring is the magnetic flux that the current generates. So that magnetic flux is captured in the magnetic core of the probe, and then you got a coil of wire wrapped around it that goes out to your output connector here. And so they are sometimes called current transformers because that's exactly what they're doing. They're behaving as a transformer. So your primary is the loop formed by your cable under test and the ground reference, and then the secondary is the loop of wire around the core, and then it gives you a potential out here corresponding to the current that caused it. And then an injection probe, it works kind of basically in reverse. You apply a signal here to the connector, and then there's the same coil of wire wrapped around the magnetic core. Then it's producing that magnetic flux that you clamp this thing around your victim cable, and it's producing a magnetic flux through that loop, and then it induces a potential on that loop, which then results in a current depending on the impedance of that loop. It looked like there was a question.
Yeah, so you're talking about unshielded cables right now, right? Just wires coupling to each other.
I'm talking in general about cable bundles at the system level. So I'm sort of representing them notionally as single wires here, but I'm really talking about primarily about shielded cable bundles at the system level.
Okay. But say there's two unshielded wires, it'd be the same thing, right?
Yeah, I mean, if they're unshielded, I mean, crosstalk is crosstalk.
So if you're saying, so if you don't treat it as if you don't look at crosstalk for a minute, and you're saying that IC equals negative IV, would that say that says that like if you have two AC cables next to each other that they'll totally, well, not cancel out, but I guess if it's in phase, the phase matters too, though, right? Well, how it's induced and the effect.
I mean, it can. I'm not sure what you're getting at.
Okay, just go on. I'm listening.
Okay. I mean, feel free to email me when we're done here.
Okay.
But yeah, I mean, the general principle holds true whether these cables are shielded or unshielded. I'm just getting into just making these measurements at this point. So you can measure what is the total common mode current coming off of any cable. And if you're talking about power cables, they are unshielded, right? But we can characterize what currents are coming off of any potential culprit cables, and then we can characterize what is the susceptibility of our victim cables of concern. But in the worst case, we can assume that our victim current is going to equal our culprit current. So, but when you make the measurements and do the tests with these types of clamp-on current probes, you don't need to make any disconnections or reconnections. You just clamp them around the cables in your setup, and you can perform them in your development lab. And I highly recommend that you do that as an early diagnostic. So this is the default limit in the GEVS application guide, just 50 dB microamps, and we generally start at 10 kilohertz and go up to 200 megahertz. If you have specific concerns at lower frequencies, generally, if they're like magnetic concerns, then you may want to consider doing these measurements down to 30 hertz. But you should, again, know thy platform, and if you've got significant low frequency magnetic concerns where those types of low currents at those lower frequencies might have an impact, then sure, consider doing the measurements down to 30 hertz. So for below 30 megahertz, we use these modified CE101 and CE03 test methods. So on the primary power leads, we'll put the current around both the send and return leads. It could be a group of leads, right? For current capacity, you might have multiple wires here, but you run around the entire bundle, positive and negative leads, and near the capacitor network for reasons that I'll talk about here presently. And then for your signal lines, for shielded signal lines, you want to put the current probe as close as possible to the access panel. And then there's an alternate method using an absorbing clamp. I'll talk about this if time permits here. But we just taking another look at crosstalk here. If you see the culprit current is going to cause some magnetic flux, some B field, and it's going to couple through a victim loop. Well, the coupled potential per Faraday's law is just d phi dt. Just looking at magnitudes here at this point. To first order, we'll assume that the B field is constant over this height. It's not, but again, to first order for simplicity, we'll assume that the B field is constant over the height. And at low frequencies, when the cable is what we call electrically short, when it's much less than a wavelength, we can assume that the B field is constant in the horizontal direction too. So the total flux is just B times the total area of the of the loop. But when it's electrically long, then the B field is going to vary as a function of the position along the cable. So as will the current. I mean, when it's electrically long, it's a significant fraction of a wavelength. So the current will have some variability over the length of the wire, and so the magnetic flux will have that, to first order, will have that same variability over Z, over dimension Z. So the total flux then is going, again, assuming that it's constant over the height, is going to be the integral of over the length of the cable of our B of Z. And so we'll get this expression here, but then we'll do a little mathemagic here, and we'll multiply by L over L. So we'll put L here with these constants, and then we'll put 1 over L in front of the integral. Well, why did I do that? Well, 1 over L times the integral from 0 to L, it gives you the average current. The average current is a function of distance. And so the inductive crosstalk is determined by the net integrated average current, not so much by the peak current. And then similarly, well, okay, when you have a constant culprit current over frequency, which is just a handy construct for just basically characterizing a transfer function, when you have a constant culprit current over frequency, then the coupled potential is the time derivative of the flux, which basically in the frequency domain means it's proportional to frequency. So as you increase in frequency, you're going to get more coupled potential. But then the victim cable impedance is mostly inductive, so that impedance of your victim loop is also increasing with frequency, just J omega L. So if you've got if you got your potential that's proportional to frequency, and your impedance is also proportional to frequency, that's going to give you a constant victim current over frequency. So for any given culprit current over frequency, if you just are characterizing it based on a constant culprit current over frequency, you're going to get a constant victim current over frequency. And from a couple slides ago, we can assume that the victim current is going to be equal to the culprit current. This is that Hertzian dipole mess that I mentioned before. You can see that these electric field components are very complex expressions, and literally complex. They're J terms. They are imaginary components here. But all this is assuming a point source. So this is the sort of thing people will sometimes use to say, okay, we've measured this at 1 meter. What's the field going to be at 2 centimeters? So this is a very complex equation based on looking at this as a point source. So anyway, the main point here is that in the far field, we can simplify the expression that really only having a 1 over r term, and then you have this constant times I dot times IDL. And the real point here is that far field emissions are also determined by the net integrated average current, not by the peak current. I'm going to skip over some of this. So, okay, let's get to transmission lines, because this is kind of the crux of what I want to talk about. So any cable from which we want to measure the common mode current must be modeled as a wire above ground. So our height above the ground is 5 centimeters per the mill standard. And so A is our cable wire radius. And in the transmission lines session, I talked about how you can calculate this, but this type of configuration is going to give you a characteristic impedance on the order of 300 ohms. And it's a logarithmic relationship, so that you know, any deviations, you know, from it's a function of h over a, you know, the height above the ground to the cable radius. And because it's logarithmic, there's a fair amount of slop. You know, the h over a can vary a decent amount, and you're still right around 300 ohms, give or take. So to first order, 300 ohms is a good assumption for your characteristic impedance of this. So again, when you get up in frequency, and we're talking about making these measurements up to 200 megahertz, where these cables are going to be electrically long, they will behave as transmission lines. So they'll have a characteristic impedance of about 300 ohms. So a typical case of a wire above ground transmission line represents a shielded cable with a shield terminated to chassis at both ends. Now we're also dealing with unshielded power cables, but when they're terminated in that capacitor network at high frequencies, the capacitors will also basically look like a shorted termination. So I think this discussion still holds. But when you're talking about a shield terminated to chassis, then you're basically, it's a short circuit, right? So basically your source and your load impedances will look like short circuits, or very close to it. So you will have a mismatched impedance, you will have reflections, you will have standing waves. And so again, all this is in the transmission line session, but you'll have your reflection coefficients at the load end and at the source end. And the end result is you're going to have standing waves on the cable. If you look at the blue trace as your send wave, and it hits a shorted termination, looking at this in terms of voltage, the shorted termination is holding the voltage at the end to zero. You can't build up any voltage across a short. So the reflected wave, the red wave, is going to be the negative of the blue signal at that point to basically give you a net voltage of zero at the termination. And so then that reflected wave starts heading back in the other direction, and the combination of it gives you the black trace, which shows standing waves. You have patterns of peaks and nulls along the cable. So this is the sort of thing that you will observe when you're trying to make common mode measurements on this type of configuration, where you've got what is essentially a transmission line with a 300 ohm characteristic impedance terminated in a short at both ends. So this is just something to pay attention to when you're making these measurements at higher frequencies. The position of the current probe is going to matter. If you happen to put the current probe in this spot here for this particular frequency, you're going to get a null, just because of where you put the current probe, and you're going to get an artificial indication that, oh, I have no current emissions at that frequency. But if you just move the current probe a little bit over here, and now you're at a peak, like, oh, golly, because I'm sure you would only say golly if it went up by 20 dB or 30 dB. But you can get a significant error in your measurement if you put the current probe in at a null, or it's going to matter where you put the current probe. So I've got a lot of math here. I think I will leave this to peruse when when you look at the charts, if you are a fellow mathicist like me. But if you work through the math, you get a very complex expression for the current along line as a function of position, as a function of Z. But you have these reflection coefficients in there. If it's a matched line, then all the reflection coefficients by definition go to 0, and you have a much simpler expression here. And so you'll have a constant current amplitude determined by the characteristic impedance of the line. Right. So in the transmission lines session, I go through, I actually derived this equation here because I'm a mathicist. But the real takeaway from this, and I go through all that in the transmission lines session, but when the length of the cable is an odd multiple of a quarter wavelength, so when you hear us talking about quarter wavelength and half wavelength resonances, this is where that comes from. When the length is a odd multiple of a quarter wavelength, the apparent input impedance that you see at that distance from the termination is going to be the reciprocal of the physical termination. So if ZL is a short, which is basically what we're talking about here, for a shield that's terminated to chassis at the far end of the cable, when you are a quarter wavelength away from that, it's going to look like an open. And it's just physics, and it's just the way the math works out. That a short circuit will look, a physical short will look like an open when you are an odd multiple of a quarter wavelength away from it. So you're going to get current nulls. It's going to look like a very high impedance, so you're going to get current nulls. At multiples of a half wavelength, then the impedance that you will observe at that distance away will equal the physical termination. So a short will look like a short. So you'll get current peaks at those frequencies. And so just looking at this analytically, and I've done plenty of measurements to show this is a really excellent model. In fact, in the transmission line session, I go through all this math, present this graph, and then I take measurements to show that that when you go on and do onto a network analyzer to measure impedance, it's spot on. That you get exactly this type of profile. And this is what I was just talking about. You get current nulls at odd multiples of a quarter wavelength, and then peaks at multiples of a half wavelength. Okay, and so if we look at an example of a 4-meter cable, so 2 meters in front of the ground plane and then 2 meters to the wall, you'll get nulls at odd multiples of 18.75 megahertz and peaks at multiples of 37.5 megahertz. So this is just a general example, just in Excel, where this is effectively frequency, but I'm doing it in terms of fractions of a wavelength, L being the length of your cable, so L over lambda. All right, so the peaks and the valleys will vary along the length of the cable as a function of frequency. So the traditional recommended way to deal with this when you're taking a measurement is in order to properly capture all the peaks, you should put the receiver and analyzer in max hold mode, and then physically scan the current probe along the length of the cable. That's if you're wanting to do it properly. I've very rarely seen anybody do this, or I've done it on some tests that I've been running personally, but giving this as an instruction to somebody is not always something that happens, right? It's a little bit non-standard, and it's a little bit of a pain if you're not really expecting to have to do this. It's not that much of a pain, really, but an alternative though is I mean, I've done this analytically, and I've done it with actual measurements. But if you just work through the math, that when you move the current probe to the far end, so let me back up a second here. And bear with me here, because this is getting into the weeds, and this may be a little it's non-trivial to explain, so just bear with me. But this blue curve, the blue dash curve, is the same one that I just showed you on the previous slide. This is putting the current probe at the EUT. So going back to this figure here, this is our transmission line. So our source is effectively our box is the EUT. And then our termination, I'm just representing that as 1 ohm here, because Excel doesn't like it when you divide by 0. But 1 ohm is a sufficiently low impedance to get the point across. And so what we're measuring is the impedance at this point at our source, which I'm calling the EUT, is the equipment under test. And then you have our cable going to a termination some distance away. So it's the impedance that you observe at this point as a function of frequency. Okay, so and so when you are a quarter wavelength away, odd multiples of a quarter wavelength away, a short looks like an open, and you will get a current null. And at multiples of a half wavelength, the short looks like a short, and you will get a current peak. It'll basically look the same as what you get at DC. But at DC, transmission line effects aren't in play. You just get your 2 volts RMS, and this is just an analytical thing I did, right? I just set 2 volts RMS into a net of 2 ohms, 1 ohm source impedance, 1 ohm terminating impedance. So I should get an amp, 120 dB microamps. So these peaks will have the same magnitude as what you have at DC. Everybody with me here? Okay, so we'll move the current probe. So this example actually is with the current probe at the EUT. But as we move it to the far end, if we move it to the load, then we bring the peaks up, right? So I'm sorry, we bring the nulls up. We bring these nulls up to what they would be into a match load. So if we're ideally into a match load, into a 300 ohm load, this will be the ideal current we should get at these frequencies, just this blue dashed line through here. So if we move the current probe to the far end, to the shorted termination, we'll bring these nulls up to basically give us the same current that we would have into a match load. But that still leaves the peaks. So that takes us a bit away from the nulls here. But so the significance here is if you put the current probe at the EUT and at these frequencies, you're going to have these nulls, which will give you a false indication that you've passed. When you could have tremendous emissions, you could have tremendous current emissions at these frequencies, but because you're looking into what looks like a high impedance, you won't observe them. And that's the worst possible result as far as I'm concerned, is that you're masking a problem simply by the way you're making the measurement. Now, you can also have a false failure when at these frequencies where you're going to get an exaggerated reading of what the current is, because now you're at a resonance at a peak resonance. These are both resonances, right? These are both a function of resonances. They just have the opposite ramification. But you're going to have a peak resonance or a null resonance. And at least here, a false failure, I'd much rather have that, because that gives me something to look at and disposition and figure out what's going on. If I'm here and don't see anything, then I proceed with this assumption that everything's fine, and I could possibly miss a very significant problem that bites me when I'm integrated on the platform. That's the worst possible result. That's why I'm painstakingly going through all this, so that you understand the physics. When you make these measurements, you got to pay attention to this stuff, because you could get bitten if you don't do the measurement properly, and you get inaccurate results. So hey Noel, looks like you have a question.
Are you arguing that the conducted emissions measurement as directed by 461 at less than 5 centimeters is insufficient?
Well, 461 doesn't specify a common mode measurement. It only specifies the differential mode measurement. This common mode measurement is in GEVs. That's what I'm talking about.
Okay.
But they talk about, I think they specify 5 centimeters for differential mode. They talk about the current probe being right near the capacitor network or the Lizens for differential mode, or standard conducted emissions measurement. And so for common mode on the power leads, making the measurement at the capacitor network is what we want for all the reasons that I'm talking about. Does that answer your question?
Well, yes, you know,
But the milk doesn't
we'll carry out this, this discussion later. Thanks. But
Sure.
yeah, correct.
You can email me.
Right.
So, about 10 minutes here, but I think we're actually pretty close to the finish line here. So with the cable shields terminated at the access panel, it's desirable to get the current probe as close as possible to that termination for the reasons that we just talked about. And for frequencies less than about 30 megahertz, you can use a standard current probe, place it as close to the panel as possible. Okay. Absorbing clamp is a kind of a controversial thing. So, but I'll talk about it here a little. So ideally, if we really, if we could specify anything we wanted here, we would want a normalized measurement of emissions that is independent of the cable configuration. So a matched transmission line would be ideal. The significance of this is that we say we want you to bring flight-like cables to your EMI test. If you bring the actual flight cables, that's ideal, but we almost never get that. Nobody really wants to drag flight cables around for environmental testing. So they need to be at least flight representative. And the main thing, it has to do with the cross section of the cable, twisted pairs, internal shielding, shield terminations, and you don't want your test cables to be better performing than the flight cables, because you don't want them to mask a problem. And so if you have the lengths of your test cables identical to your flight cables, again, that's ideal, but that's also not always achievable. You may be building your test cables before you know how they're going to lay on the spacecraft, and you may not know the exact flight lengths. So what that means is that this pattern of peaks and valleys that you get in your test configuration might be different from what you have in flight. And there's not much you can really do about that. If you're building test cables before you're building flight cables, that's just kind of the way it goes. And so you just need to be aware of that difference or that limitation. So this pattern of peaks and valleys could look different from what you actually see on the spacecraft. So the ideal thing is if we could actually make our cables behave as a matched transmission line, so that we can get a normalized measurement of just the inherent emissions coming out of the UT that's independent of the cable configuration. So again, this will, yeah, okay, that's pretty much what I said here. So at our odd multiples of a quarter wavelength, where the apparent input impedance is the reciprocal of the physical termination, if we were to increase, where we're typically talking about a short, the shield terminated to chassis, if we increase that impedance, and this is all speaking theoretically for the moment here, so just bear with me, but if we increase that short, then it will reduce the apparent input impedance observed at the far end. Okay, so it will increase the current at the nulls. Likewise, if we increase our half wavelength resonances, if we increase that shorted impedance to something closer to the characteristic impedance, we'll increase the apparent impedance at the far end, and that'll decrease the current at the peak. So it'll detune these resonances and get things closer to the what the ideal current would be into a matched load. That's what damping is. It's detuning the resonances. So I've got a lot of mathicism here on the next several slides. So I think I'm just gonna, in the interest of time, I'm gonna go past all of this. You're welcome to look at this and email me questions. But what I will mention here is that if you actually put a matched termination at all frequencies, that would reduce the current emissions at lower frequencies when the cable is electrically short. That's not desirable. We don't want to artificially reduce the current emissions at low frequencies. And also inserting such a connection, if we were to actually put a 300 ohm resistor in series with our cable shield termination, well, that's breaking the shield termination and, inserting a 300 ohm resistor. That's neither desirable nor practical. So enter the absorbing clamp. This is a device that's been used for years, for decades in CISPR 16. It's a current probe followed by a set of ferrite ring absorber elements, and it adds a resistive impedance above about 30 megahertz, which it's basically a damping resistance, and it basically provides that function of providing at least approximately a termination that comes close to the matched impedance of your transmission line. And this absorbing clamp was specified for the space shuttle program to address radiated emissions below 200 megahertz. This was actually included in the RE102 section of the space shuttle document, as a test method for radiated emissions. But it really is a common mode conducted emissions measurement. So in GEVS, I put it as in the conducted emissions section. But anyway, this is just showing how you would hook it up. And we've taken some measurements with this here. That this does show that the absorbing clamp will affect the current measurements below 30 megahertz. So I don't really recommend we use it there, but above 30 megahertz is when it's most effective. This is really, I think, the picture that shows that. This is the measurement with a standard current probe when we're looking at the source end. We have our pattern of peaks and valleys, and we use two different absorbing clamps here and show that we get that more normalized mid-range level here that's basically isolating us from the rest of the cable, and we're not seeing the resonances from the cable configuration. We're just getting a more normalized measurement of what's actually coming out of the EUT. And another way of looking at this is when we have either a shorted termination out here or an open circuited termination out here, we get basically the same results, whatever that termination is out here. So again, that damping resistance, that damping impedance of the clamp basically isolates you from what's happening, at least at the higher frequencies, isolates you from whatever's happening on the rest of the cable, including the termination. So it's just another indication that it gives you a more, I'll say, normalized measurement of what is inherently coming out of the EUT. And then we'll actually demonstrate some of these measurements when we get into the lab next week. So that actually brings me pretty much to the finish, at least for this portion. Just a couple summary statements. We don't generally do RE102 below 200 megahertz. It's not needed or useful in Goddard programs. We do common mode conducted emissions measurements on cables. That gives us a much more direct and efficient tool for assessing the crosstalk risk at those frequencies. For a typical case of a shielded cable with a shield terminated to chassis at both ends, the cables must be considered wire above ground transmission lines with shorter termination at each end. And that current distribution will exhibit a predictable pattern of peaks and nulls. Nulls at odd multiples of lambda over 4, peaks at multiples of a half wavelength. And that's just physics. I mean, that is what you will see. And so just knowing that physics and knowing the math will help you understand that and know what you're looking at when you see that on a spectrum analyzer or a network analyzer. So for a low impedance termination, a shield cable terminated to chassis for signal cables or the capacitor network for power leads, the maximum current will occur at the termination, so the far end from the EUT. When using a standard current probe, place it at the load end to ensure that the peak current is captured. So that's at the feed-through plate for shielded signal cables or the capacitor network for power leads. The absorbing clamp is an alternate option at higher frequencies, so nominally above about 30 megahertz. But if you look at that impedance curve, that nominal impedance curve for the absorbing clamp, the inserted impedance is mostly resistive starting at about 30 megahertz. Below that, it's adding more inductance, and that's going to that's going to be a little bit less controlled. And you're mainly what you want is the added resistive impedance, not the added inductance. But it measures the approximate average current and gets closer to an ideal normalized measurement of EUT emissions that are independent of cable configuration. Again, there's no requirement to use the absorbing clamp depending on where you go, but it's an additional tool in your belt. You know, I always say that when you have an additional tool, it doesn't have to replace anything that you already have. The standard current probes are still great. Don't get rid of those if you get an absorbing clamp. Just, you know, and we generally use the standard current probes for these measurements, you know, for most of the tests that we do. And then the absorbing clamp is just another tool in our kit. If we see something a little strange with the standard current probe and we want to get another look at it with the absorbing clamp. So, and these measurements can and should be performed as an early diagnostic in your hardware development lab well in advance of official EMI testing in the anechoic chamber. They're very quick and easy to perform with these clamp-on probes requiring no disconnections, and they provide invaluable information to help you identify and diagnose potential problems as early as possible in your product development flow. There's gory details provided in the section of GEVs shown here. That's what I have. I can hang around for a few minutes if anybody has any questions.
Yes, I got a question. And GP 11461, they use the absorber clamp and CE 104 all the way down to 150 kilohertz. What do you think about that? I mean,
Oh, that sounds very similar to what they borrowed that from the space shuttle spec. I mean, I think it's a lot of the same people developed that GP doc. That's a gateway document, right?
yeah,
Yeah, I was just, who's that speaking, by the way?
Ron Coleman.
No, hey, Ron. What center are you at?
I'm over at Johnson.
Okay. So I don't know if you've met Bob Scully, but Bob had a lot to do with defining that absorbing clamp method in the space shuttle spec. But yeah, these measurements below 30 megahertz that I was showing back here.
Yeah, I saw that.
Yeah, it's and now if you're measuring something that's behaving as a true current source, an ideal current source, then whatever inserted impedance you're putting in there shouldn't really affect things too much. And next week I'll show, when we go into the lab, you know, I'll show some measurements with the absorbing clamp compared to the standard current probe, and at the low frequencies, at least for this source that I'm using, the levels don't change all that much. But here I'm using a voltage source. You know, I'm just using a signal generator with a constant potential. But with when I insert the absorbing clamp, and specifically when I use two different absorbing clamps, I get two different levels at the lower frequencies here. Above 30 megahertz, you know, the results are much more consistent. But this is what gives me pause about using the absorbing clamp down to 150 kilohertz. You know, I would probably want to do a measurement with a standard current probe for comparison. That's my preference anyway.
Yeah, it seems to not make much difference, right, on the dampening. So
Once
why
you're
use it, right?
It's really damping, right? If we go back to, you know, here, and this is just a typical, you know, it's a representative curve, right? This isn't a universal curve, but the general general thing, excuse me, the general profile here is so X. This is the reactive contribution to the impedance, and then R is the resistive contribution. Z is the total impedance that's being inserted. So at the low end, at the low frequency end, that's starting at looks like a megahertz. The Z the total impedance is pretty much right, is right along the same curve as the inductive reactance. So the inductance is dominating down here. Then as you get up about a little above 100 megahertz, am I looking at that right? I'm sorry, 10 megahertz. Yeah, that's 10 megahertz, 10 to the 7th.
see.
So up around here, up around 30 megahertz is where the total impedance is dominated by the resistive component. That's where it's doing more of the damping or absorbing. That's where it's absorbing or dampening out those peaks. So down here in the lower frequency range, you're in the more inductive part. I mean, they're ferrite beads. They're going to be inductive. And that's where the additional impedance inserted by the clamp can have an impact on your measured result, just depending on, you know, whether your source is acting more as an ideal current source or as an ideal voltage source. And you don't really know which one, right? If you're just making a measurement on some EUT and you don't know the innards of the EUT inside and out, you don't really know if it's acting as a voltage source or a current source. But I can see in this example where I know what I'm applying is a voltage source, that added impedance is affecting the current that I'm measuring.
John, and
Yeah.
I think for the audience, we need to clarify that per CISPR, the absorbing clamp works on an EUT that has a single conductor. CISPR 16 is for drills, microwave ovens. If you have an EUT that has multiple conductors or cables, each of those cables needs an absorbing clamp installed simultaneously. And it's just because it changes the current path when you insert the resistive series.
Which illustrates that using the absorbing clamp can get a little complex, and you know,
And it is a great tool.
yeah. But yeah, you need to do a bit of homework if you're using the absorbing clamp, because it can influence the measurements that you're taking. We don't have a whole lot of time to prolong this, but I'm happy to entertain any questions over email, or maybe we can have a separate conversation just about this. But our general approach, like I said, is we'll use the standard current probe as our going in position. And, you know, if you're talking about early diagnostic testing in the lab, standard current probes are much more portable, right? We can bring standard current probes anywhere. I mean, we can bring the absorbing clamp anywhere too. It's got a little carrying handle, but it's bigger, right? This thing is about, not quite a meter. It's maybe 60, 70 centimeters long. And just in a lab setup, it's a little more cumbersome to get that thing in place to make current measurements. I mean, you can do it, but just with a standard current probe, you can pretty much clamp those around any cable you're concerned about. So certainly for early diagnostic measurements, a standard current probe is fine, just with the caveats that you may be dealing with peaks and valleys. So if you see something like this, just understand that's what you're going to see when you have a mismatched transmission line and standing waves. Now, by and large, I think like when you get up in the higher order harmonics really tend they will decrease with frequency. So when you get up into, you know, many tens of megahertz, hundreds of megahertz, most of the time we don't see a whole lot up there. So even if you're getting an exaggerated reading due to cable resonances, a lot of times that's still compliant with the limit. And, you know, if you're getting a worst case measurement and you're compliant with the limit, then you're done. But if you're getting some of this type of behavior where you're not meeting the limit at high frequencies, I mean, you can get out the absorbing clamp and take some additional measurement for comparison data. But just be careful if you're using the absorbing clamp, and just do a bit of homework to understand what you're seeing with it. I hope all that helps.
Yes.
Okay. Anybody else have any questions before we wrap up? Okay, well, thank you all for participating. Thanks for hanging on for an additional few minutes. And I'll get the recording and the charts posted. The charts are actually already posted from yesterday, but I'll get today's recording posted as soon as it's available. So thank you and have a good day. And we'll talk to you next week when we go back into the lab.
Thanks, John.
Thank you.
John.
Yep.